Hi everyone, this is Rishi here, a customer engineer from Google Cloud, and today I will be talking about streaming analytics with dynamic schema, which is a very interesting problem, and let's see how we can solve this together. So before we go dive deeply into the problem, we will just try understanding first what is streaming analytics, how a framework like Apache Beam solves some of the streaming problems, what the dynamic schema problem is, how we can solve this particular problem by a particular approach, and then I will show you a demo of how it has been implemented in the code. So again, this is just a big list of all the machine learning, AI, data, and rightly it's called a mad landscape. So we're not going to dive deeper, but just to showcase the number of companies, number of products coming in this particular landscape is just huge. So talking about streaming, one thing we have to understand is streaming means continuous flow of data, right? So it's unbounded data and there is no limit of the data coming in compared to a batch where you are storing the data in a particular repository, be it blob storage like GCS or a database, right? And if you see this diagram on the right hand side, you see a pipeline, and what does a pipeline contain? One, it will have the sources from where we have to read the data. For a streaming use case, it can be a messaging queue like PubSub or a Kafka. Then you have various transformations, aggregations you are performing. So typically you see P transform, right? And then the data gets stored in a particular collection. And finally, after you have done your processing, you would be writing it to a storage, be it a data warehouse, a database, or a blob storage, right? And that storage is called a sink. Then in streaming pipeline, some of the concepts are there of windowing. You have fixed windows where you are working on a fixed span of time, like 12 AM to 12:05, then 12:05 to 12:10, right? Might be in a gap of 5 minutes. The sliding windows, you are also having a fixed period. So just think about how you slide the windows, right? So you are sliding the windows and collecting the data. The third very interesting piece is the session windows. So typically for a website, let's assume an e-commerce website where a customer is just going through a website, clicking on products, adding those in the cart, doing a checkout, right? And you want to track the journey of a customer. So in those cases, you will be looking at session windows, and session windows typically the way they work is they would be collecting all the information of a particular session till there is a gap. So you would have defined that might be the gap is, let's assume 20 minutes. So if no data is collected within 20 minutes, then the session will stop. A very important concept to know here is also of event time and processing time. Again, this is a little confusing, again when I have talked to multiple customers. So what we have to understand here is the event time is the time when the actual event happens, right? And the processing time is when the event has actually been consumed by the processing layer or when it has arrived in the processing layer. So let's assume you are playing a game and then suddenly you went through a tunnel and you don't have a network, right? So as soon as you come out of the tunnel, when your network connectivity is restored, the data comes to the processing layer. So event time might be 12 AM. When it reached the processing platform, it can be 12:05 AM, right? So these both are different. Then for the unbounded data, again there are multiple approaches. One approach can be time agnostic. You are not bothered on the time. Typically this will be a scenario where you have data coming in and you have to filter the data. So might be you are getting malicious packets also coming in from your network and you just want to filter malicious packet and only the good packets should go to a processing pipeline. So you are not bounded by time, but you are time agnostic. You might be required to do some approximation based on the data that you have, might be what products are trending even if you don't have all the data with you. So typically you would have some approximation algorithm being used. Then based on event time or processing time, you can do your windowing. Right? So there are some drawbacks of event time processing. So as I said, the completeness, because it might happen that the event might not have reached the processing layer, and it might have some problems with the accuracy of the data. We will talk more about it, but that is how typically it works. Right? And if you see, this is how the evolution of large scale data processing has happened, with a MapReduce paper coming out I think in around 2004, and then gradually Hadoop, Flume, Spark, Kafka, Dataflow, Beam coming into the picture. Right? So what we are going to talk today is more on how we can solve problem with Beam. Right? So if you think about a typical scenario, right? Going a little back, you typically would have seen a Lambda architecture where you would be having a streaming layer. Typically you would have Kafka, and from Kafka you would have a Spark streaming job running in, and then let's assume you are doing aggregations. The aggregated results are stored in a database. The problem here is the completeness or the accuracy of the data. And as I said earlier, you might have some data that is coming late, right? So those data will be captured by your another layer, which might be a Hadoop layer. So that batch layer gets executed again every night. So you have the completeness of the data. So if you see the problems here, one, you might be having a different infrastructure for both of these solutions, Spark and Hadoop. You might have a different set of team doing this computation, processing, as well as managing the entire infrastructure, right? So wouldn't it be great if we can have a unified or a combined framework which can execute both on batch and stream, right? And this is what I'm talking about. Instead of having a different batch and streaming framework as well as a branch, it will be great if a model, which is a unified model, can solve in a same code base both these problems, right? And that will be one of the best thing. You have a single infrastructure, single pipeline, single code base handling both of these things. And that's where Apache Beam comes into picture, right? So Apache Beam helps you develop in your favorite language, be it Java, Python, Go SDK also has recently come, and then it works for both batch and streaming processing. And also you're not bounded where to run this particular pipeline. You can run it directly on your laptop, you can run it on a managed service like Dataflow, on Spark, Flink, Samza. Again, you have multiple runners. And to see the compatibility of the runners, you can look into the link that I have provided just to see what all capabilities are available in a particular runner. So just understanding a little more on how the batch and streaming stuff are different. So if you see, taking an example, you have to do an aggregation of your data, and let's assume the batch job starts every night, and you have to get an accumulation of the information of, let's assume, how many products are sold today, right? So in batch case, every night the job runs, right? It loads the file, let's assume from a blob storage, does the computation and writes a result to a, let's assume a database. In a windowed batch, let's assume your use case is for every hour, you want to now see how many products are sold. So what you will do is, the same files you would read, but now you will segment this file into different batches. So you create a windowed batch of 1 hour, do the processing of those data by just, what you do, you just sort the data into a time frame, take each hour data, do the processing, accumulate for 1 hour, and then write the results. Coming to more real-time streaming use case, right? So what happens here, since the data is coming in, let's assume you have to do just accumulation of 2 minutes, right? In this use case, you have data coming in. But as I said earlier, the problem of late events still are there, right. So, it is possible the event which was generated at 12:02 comes to you at 12:03, right. So, how do you determine how long you should be waiting for all the events to arrive for a particular length of window? Right. So, data flow helps you there by giving you something called as watermarking. So, based on heuristics, it tries to understand how much time it will take to get all the data for a particular fixed window, right. So, it will wait for a particular duration of time before it does the computation, right. But still there is one problem. The problem is, even after heuristics, it is possible, let us assume the event comes after 5 minutes and heuristics just waited for another 2 minutes, right. Like I gave you a tunnel example, or you can think about an airplane. When you are going and boarding an airplane, after a couple of hours the flight lands and the data is synced, right. So, you have to think then, can you lose that data? Would it be fine to just remove the data in your processing? But for some of the transactions you can't miss that data. It would not be the completeness of your aggregation. You might have an incorrect aggregation, right. Then you have something called as streaming plus accumulation, where you are able to say that wait for this much duration, even wait for a few hours, and then with the data that has come, do a reaccumulation. So, you are able to gather the data which came late, right. So, that is what is called as streaming plus accumulation. So, one interesting factor is when you are running it in a managed service like data flow, you also get a lot of new features, what I would say, like optimizations, graph fusions, windowing, right, watermarks, triggering, what I showed you, like accumulation stuff, right. So, you are not required to do all these things. Even let us assume you are running a job and you have 10 workers doing a particular job, right, and one worker there is a laggard which is taking a lot of time. So, dynamically data flow has the ability to even understand which is a laggard and take the work from that particular worker to and split it into other workers, so that the job can be completed faster, right, because ultimately you are paying by the amount of time the CPU and the memory are being consumed. So, just to dive a little more deeper, so you are more clear on the windowing concept. So, if you see this GIF, right. So, the fixed window here is from 12 to 12:02, and if you see this green line that is going upwards, right, that is the heuristic benchmark which data flow has derived based on the actual time when the event is reached to a processing or the data flow layer, right. So, if you see, based on heuristics might be the events that came by 12:02, it will wait till 12:06 before it processes the event. So, if you see the window of 12 to 12:02, it waited for 12:06 and then you got the aggregation as 5, right. But what if the events come beyond 12:06, right. So, if you see here, it shows about event coming it later, right, and then a reaccumulation is done for the late events, because it is streaming plus reaccumulation, so that you get the accuracy of the aggregation. So, if you see the number increased from 5 to 9, because it was able to accumulate the late arriving events also. One more interesting problem that data flow is solving you is exactly once processing. So, you do not have duplicates that are there in your final sinks, right. So, if you see a typical pipeline, you would have sensors, log data being pushed. So, you would have a client which gathers this data and pushes to a messaging queue, let us assume PubSub in this case, and then the processing happens in the next layer, which is the data flow layer, and then finally after processing the data is stored in a storage like a data warehouse like BigQuery. So, there are some places where a developer has to take care of duplicates, but in some of the scenarios data flow is able to do snapshots and remove the duplicates. So, if you see source generated duplicates, when you are writing it or publishing it from your code, you have to take care as a developer to remove the duplicates. Once it reaches the data flow pipeline where you are reading it from PubSub, processing data in the data flow, right? Data flow would be able to take care and remove those duplicates by its checkpointing mechanism and some other algorithms, right? Like deduplication. Writing through a sink, it depends. If you are writing to something like a BigQuery, there are ways how duplicates can be removed. Else, the writer of a sink has to take care how the duplicates will be handled. More details below in this link if you want to get more details on how duplicates can be resolved in a pipeline. Cool. Now let's come to the actual problem we were thinking about, right? Which is a dynamic schema problem. Very typical problem. You have built a pipeline and everything is working fine. Till the point of time your pipeline starts breaking. And why is it breaking? There was a business requirement where some new columns were added, and while you are reading the pipeline, you are applying some transformations and writing to a sink. Because of the new columns, the sink gets broken, and you are again seeing multiple errors that schema is not matching or columns not found, right? So what typically is done might be you stop this pipeline, you manually go to the sink, add new columns, rerun the pipeline, right? Another scenario is if you are having schema in your code, you will modify your code, you will add these new columns, again following the entire CI/CD pipeline. Again, I would say which consumes a lot of time. I would say typically wastes a lot of time because you will do a check-in of the code, test of the code, then you would do a merge of the code, review of the code, finally it goes to master, and then it will be sent to the actual production pipeline. Apart from that, this also would cause delayed or incorrect metrics which will be seen by the business. And let's see how this typical streaming pipeline looks like, right? Then the pipeline that you have created. So if you see, you have events coming in, right? You have, in this case, Cloud PubSub, which is the messaging queue. In the code that you create in the Apache Beam pipeline, you are using PubSub.io to read the data from this streaming messaging queue. You typically would be parsing the packet that has arrived, the string packet, convert it to JSON. You might be doing some filtering. You would then, if you want, you can do some transformations, processing based on your business rules, and then you would be converting it to a schema, or a schema which this sink would understand. In this case, a table row with schema which BigQuery would understand. And then let's assume you have a use case based on a particular attribute value, you want to write the data into different tables, right? So in that case, you would use something like a dynamic destination inside your BigQuery IO and then write it to BigQuery. For any errors that are encountered in the pipeline, you would be storing those errors into a cloud storage, right? So let's see a quick demo so you understand how this code also looks like. So let's go to our favorite code editor, and then if you see here, this is the pipeline I was talking about, right? So just looking at this part of the code for now, you are just reading the messages from PubSub.io. The P collection is a parallel collection. You have a parallel collection of string which can again reside into multiple different workers. This collection which you see as part of lines, you typically would be doing processing, and you see the pardo is something like a parallel processing which can happen in multiple different nodes. Let's go inside this dynamic JSON process. So if you see here, what we are trying to do is just converting this message. You would get this message, individual message, into a context element, and what you are doing is first converting it to a map object, right? We will look into this retry processing row later, but typically what you are doing is After you have created this map object, you would convert this into a JSON object. You might add any new property you want to, you might do filtering on that particular stuff when you are iterating the entire data, and then the final output of this JSON, you write it to your context output, right, which again becomes a parallel collection. Now, if you see here, we have a table row with schema P collection created, and this collection we are trying to now sync it to BigQuery. So, what we are using here, if you see, is BigQuery IO. We are using dynamic destination, and if I expand this further, you would see how it's able to get the table details where a particular row will be stored. So, based on the table specified in our entire metadata, those particular rows will be going to specific tables, right. One more thing to see here is you have some create and write disposition. What these means is if you don't have a table, the table will get created. Write disposition is you want to overwrite the data in the table or you want to append the table, right. We are using streaming inserts, right, and we also are getting the error information, right. This is very important in our next part where when we are trying to do the dynamic schema changes, right. So, let us go and see how this pipeline looks like, and let me run the pipeline. So, if you see here, let me go to my IntelliJ, start this particular pipeline from my local laptop, and what you would see is the pipeline getting built and the jar files or the packages getting created being deployed to your backend, which is just in this case it gets deployed into a cloud storage. So, if you see here, it is uploading files to the staging location. After this uploading is done, the pipeline would get deployed into data flow. So, if you see here now, we do see a pipeline, and if you see the elapsed time is just 1 second. So, this is the new pipeline that has been created. Let us go deeper into this pipeline. So, if you see here, data flow gives me a beautiful DAG. The same steps that I had in my code are now shown in this particular pipeline, right. On the right hand side, you will get the details of the pipeline, which SDK version, which region, worker location, which can be configured when you are running your particular pipeline, right, and also how many CPUs, how much memory, all these things. And one interesting part of data flow is it also automatically can scale up and down based on the amount of data coming in, which is again very interesting. I do not need to manually go and increase the number of nodes or reduce the number of nodes, right. So, if you see what we went through the code, it was reading from PubSub, we were converting the data, filtering the data, converting it to JSON, we convert it to a table row format, and then finally we do the insertion, right. So, this was the only part of the code that we just saw now, right. So, if you see below here, it also shows you the logs. So, first you have the job logs, just to be sure everything is working, like the job has started fine, everything is all good. Then you have the worker logs for all the logging that you have implemented in the worker nodes, right, or in your code. So, here typically when the pipeline starts and the workers are provisioned, you will start seeing the logs here. And what I have seen is typically 2 to 3 minutes what it takes for the worker nodes to be up and all set for processing the data. Let us go also to our data warehouse, just to be sure we do not have the table where we are trying to create the data. So, let us go to BigQuery here, and inside BigQuery where we are trying to write. Okay, so one thing I missed showing you is all these properties are configured in the application properties file, and you would see here where we are trying to write, where we are trying to read, all those details, right. So, all those details are captured in the properties file. So, in this case we are trying to write in a training data set, and the table name we are trying to write is called dynamic events, which if you remember, right, which saw the code for that. So, right. So, if you see dynamic events is the table we are going to write, and this currently is not present. Right. To also push data, we would need, again, either we can push data through a client. In the actual scenarios, it can be directly coming from the apps and all, but just for now, for this demo, we will just go to a service called pub/sub. We go to the specific topic, in this case pump topic, and then manually we will be pushing the message. So, I go on publish message, and I have this particular message which I want to push. Let us see this message. It's just a JSON array, it's just a JSON having an array, and it has a name, age, and city state, right. So, let me publish this particular JSON packet. Going back to data flow now, let us see if I am able to see some logs. Cool. Looks like the workers are started. Let me reduce this so you are able to see it more properly. And if you start seeing, we did receive the packet. You see this log message which is there as part of the code, converted JSON. You also see BQ write schema, it is trying to create a BigQuery table, right. And then let us see if the table is created. Let me refresh this screen. Going back to my training data set, we do see a dynamic events table getting created, and if you see, right, name, age, city, state is there. There is one more column which typically we will talk about later, but these three columns are created. Let us preview the data. So, if you see, the data also is inserted, and you have city, state which is an array. So, automatically, even without specifying the schema is, as we saw, we converted from Avro to BigQuery, the schema is taken and the data is inserted. Now, let us see what happens if I provide another JSON. Let us assume it has a struct in it. So, address is a struct. So, let us go back, publish another message. Right. So, I publish another message just to see here, this is a new field that I am going to add, and also it is not a simple integer or a string field, it is a struct. So, let me publish this message. So, how do we now handle this new column that is part of my packet? So, let us go now to the solutioning piece, right, handling this new column. So, looking at this diagram now, right, lot of things are same. So, till the point we were pushing it to BigQuery IO, everything was same. And if you remember, we had one more parameter while we were writing it to BigQuery to get the extended errors, right. How this extended error helps is it provides us the details of the error that is encountered while inserting it to BigQuery. So, what we can do now is we can get all those errors which we got while inserting and classify them. So, if it is due to the schema change or a new column that was added, we take a collection and do further processing. For all the other errors, we push it to another, let us assume a storage bucket, which can be analyzed later by the team. So, for these errors which were part of the schema change, we collect all these errors. We then, what we do is we group by them into the common columns which were modified, so that the same column we do not repeat. And then what we do now is compare these columns with the existing schema in BigQuery. This is the interesting piece. So, all these unique columns which were added, which through an error, which we will compare with the target BigQuery, and all those columns and their data types, we will create dynamically new columns now in BigQuery, right. So, after these new columns are created, it might take a little time for this propagation to happen in all the BigQuery nodes, right. So, what we are doing is we are now pushing back these messages which failed due to wrong column or incorrect schema back to our PubSub messaging queue, right. And this is where the retry processing comes into picture. Remember, we had this retry processing column added. So, what the code understands, and if you see the code here, if you have this retry processing row and the count is greater than 0, it will just, it won't do any filtering again, any of those things. It will just directly take this packet and try reinserting this packet, right. And if you see how this is done in the code, so we are getting all these failed inserts, right. And you see here we are applying mutate with schema. If I go further, sorry, deeper here, you see a class called fail insert to row table row with schema. We further go inside, and if you see, here is where we are classifying whether it's because of the schema change or something else. So, if there is no such field error, it means a schema change, otherwise it's a different error, right. So, we have two different collections for that, right, and we are creating a fail schema tuple tag. We are creating a collection for only these rows, right, and in the schema mutator you will see we are getting all those rows, and then what we do here is send these schema modified rows back, oops, right, and then we are writing this fail rows to PubSub, right. And if you see, going back to our pipeline, this is where the interesting piece is. So, if you see here insertion, we get all the errors, we mutate the schema, we just print message, so we are sure, again this is just for the demo, and then we are writing it to the PubSub. Going back to our logs, so if you see here error during insert, this is what I was talking about, you are seeing no such field, right. So, might be there looks to be two new fields that were added, one is full name, there will be one more which will be on the address, and what you see here is, I am just searching for the retry here. So, if you see here retry processing row also is increased. So, let us go back and see if there has been any change in our schema first. Let me refresh this page. So, if you see here, you have full name which got added as well as the struct that is added, and if you see struct, it has a city and a street. Let us go to preview, and if you now see in preview, there is one more row that is added, and if you see here, this is the struct I was talking about, sorry, not this one, this is the struct I was talking about, the address which has a city and the street, right. And you also have this full name column that is added, right. So, just to showcase in the logs, so if you see here, what I have seen is sometimes it can take multiple retries for this insertion to happen, and this is because the propagation of the schema changes takes a little time. So, this is how I have been resolving, because again if it takes time, you again do not want again to modify the schema, right. So, you just keep pushing back to pub/sub, let it follow the same cycle, and gradually the insertion would happen, right. So, coming back to this diagram, hope this made sense. So, again doing a little recap on how this was done till the point of insertion is all clear. When the error occurs, you just capture those errors which are schema change errors. You compare the schema with the target, update the target with your updated schema, write the rows which have the schema modifications back to pub/sub, so that the same pipeline goes through and finally the rows get automatically inserted to BigQuery, right. And we just saw a demo also how this is done. Cool. So, just to do a quick recap of what all we covered in this entire session, right. We first understood what a streaming pipeline is. We understood typical difference between batch and streaming. We talked about windowing. We talked about streaming. We talked about accumulation, watermarking, how the entire pipeline looks like, how can you have exactly once processing, and we talked about the interesting challenge of how dynamic schema, the schema which is changing every day, every few weeks, how that can be managed without you modifying the code, redeploying the code, retesting things, right, and without wasting a lot of cycles, and have a pipeline which can cater to this particular dynamic schema stuff, right. So, hope it made sense. Now, thank you for being so patient, and now I am open up I'm open for questions. Thank you.